By now, I suspect you're starting to be a little tired of building linear models based on spatial coordinate data. That's kind of the example that we used for a lot of our tutorials on linear modeling. And there's a reason for that, right? That reason is that linear models, of course, make very strict assumptions about how data and the residuals of those data are distributed. And these assumptions basically necessitate that your data are normally distributed, and therefore that your residuals are normally distributed. However, a lot of data in the real world is not actually normally distributed. Spatial coordinates, like latitude and longitude, or kind of localized versions of that same idea, they're one of the few types of data that we work with as archaeologists and anthropologists that might actually be reasonably modeled using a normal distribution. There's a 0 point. You can go above it or below it. It's continuous. It seems to meet the assumptions at a base level of normality. But a lot of other types of data that we work with do not, right? If you're working with measurements of an object or a bone, for example, measurements are bounded by 0. If you're working with proportions or percentages, those are technically bounded by 0 and 1. If you're working with count data, right, those are not only bounded by 0, but they also are not continuous. They're discrete values. And so a lot of these other types of data that are actually really common, the most common types of data out there, these are not actually normally distributed in the strict sense. And so now we're going to learn what to do when we encounter those types of data and when we have to model those types of data. And we're going to do this using generalized linear modeling. So let's load in a data set that we can use. The Goldman data set is a CSV that I've made available to you. It was collected by a guy named Ben Auerbach. You can also download it on his personal website, along with metadata files to understand what all of the column headings mean. And basically this is a data set of a bunch of different individuals, skeletons, from across the country. I think 1,500 plus different individuals. Ben Auerbach took measurements on a lot of the elements and has it all included in this nice spreadsheet for us. And so let's start off with by investigating kind of some of these options. So we can look at, for example, the head and pull up the first 6 rows. Now this is a huge data set, so it's going to be a bit confusing of an output. But you can kind of see that we start off with institution that the skeleton is kind of housed in, curated in, an ID number, sex, age, a note about where it came from, more broad location, the presence of certain elements we've got, and then measurements start, and a bunch of other different indices are calculated at the end. So there's a lot of data here in this data set, right? We can see it's 1,538 observations of 69 variables. That means 1,538 rows and 69 columns. Big data set. So let's start off with by investigating, for example, LTPB. Now what this stands for, if you open up the metadata file, and I've got that linked in the accompanying PDF to this tutorial, this is the column in the data set that refers to the left tibial plateau breadth. So the top of your tibia, the tibial plateau, the left one in each of these individuals, Ben Auerbach measured the breadth of it. So we've got a linear measurement, which I believe is reported in millimeters. And let's try to see what's going on with this LTPB variable, left tibial plateau breadth. Let's model that as a function of the crural index, which is a kind of ratio of your lower leg, your tibia, to your upper leg, your femur. Kind of a measure of proportionality in that sense. So let's make a plot then of these data. Let's do LTPB as a function of crural data equals Goldman, and here's our plot. Now in this plot, it doesn't look like there's much going on. This looks like just a circular kind of scatter of point values. So I don't suspect that there's going to be a very strong relationship here, but we should still model it to see if we're interested in this kind of thing. Before we model this, I do want to clean it up a little bit, because if you look in the output here, there's a couple NAs, missing values, in this data set, and I want to get rid of those. Plotting it and modeling it will most likely be able to handle the NAs, but it's often good to just handle these up front, because some other things that we're going to do, they might pose a problem. So here I'm going to use the subset function. I'm going to subset the Goldman data frame, which is what we loaded in, and I'm going to subset it using this function called complete cases, complete.cases. I want to make sure that the LTPB column has only complete cases, meaning that there are no NA values there. And I also want to run complete cases on the Krull index. And so if I run that, we've now eliminated the NAs. So there's just a handful of those, but we've gotten rid of those rows now. So now that we've cleaned things up a little bit, I just want to illustrate for you what a regular linear model would look like applied to these data. A regular linear model making the assumptions of Gaussian distribution of data using the LM function. So let's do LTPB as a function of Krull, and the data is the Goldman data. So now we've got our bad model there. Let's inspect the diagnostic plots, right? To see how exactly we might be violating the assumptions of a linear model, right? And interestingly, in the case of these data, right, these measurement data, our residual plot here looks pretty good. It looks like our residuals are normally distributed. If we move to the next plot, we've got a little bit of deviation from normality at high and low values, but the QQ plot isn't terrible. Most of this is falling along that axis, pretty normally distributed. This standardized residual plot, again, it doesn't look like there's any heteroscedasticity here. The residuals versus leverage plot, right? We can't even see the Cook's distance confidence intervals, so it's looking like there's no undue influence of any point over the shape of the model. What these diagnostic plots are telling us is that this model, right, seems to be fitting well, right? There's no kind of heteroscedasticity. We've met that assumption. It looks like the residuals are normally distributed, at least according to these plots. It doesn't look like there's any weird kind of interdependence issues with the residuals. Doesn't look like there's any nonlinearity going on. Things seem okay, but this is a bit misleading because you need to take a step back and think about your data, right? If you just look at these diagnostic plots, you might erroneously conclude that you could use a linear model on these data. And to be sure, you probably could and get away with it, and it wouldn't make that big a difference, at least in this specific case. But, all right, there is a problem with using a regular linear model to model these kind of measurement data. And to see that, let's go back to our plot, LTPB. It's a function of Krull, data equals Goldman. So we've got our plot here, looking like there's no real relationship. But now let's add that linear model fit. And we'll add it in red so we can see it. All right, straight line running right through. Doesn't look like there's much of a pattern going on here. But that model, again, looks reasonable, doesn't it? It looks like it's fitting those data pretty well. But as I said, there's a problem. What if we extend the plotting dimensions? Let's say y-lim, instead of being kind of a range from, 55 to 85, more or less, let's run it from negative 50 all the way up to 90. And let's run our x-lim out as well, from 0 to 10, let's say. If we plot these data now, right, our plotting window is huge, and our data, that little cluster of points, is now way up in the top left. Let's plot our linear model fit. And look at that. This linear model fit is doing what all linear model fits do, extending from positive to negative infinity in either direction. It just keeps going, right? And you'll notice that 0 on the y-axis, right, a LTPB value of 0 is right here. And this red line crosses that 0 line and continues into a negative direction, right? How can you have a tibial plateau that is a negative 40 millimeters in breadth? Right? You can't. That doesn't make any sense. This is why we talk about measurement data being bounded by 0. You can really only have positive measurement data unless you're doing a weird calculation on it. And so this linear model here is really kind of a bit silly. Now, for our purposes, because the data are so positive, when we're zoomed in on it, we can't really see that this model is going on forever, and it's really not a huge problem in most cases. But it is unrealistic, right? And this is why using a linear model for this type of data is actually violating the number one assumption of linear modeling, that your model needs to make sense. It needs to make real-world sense. It needs to make biological sense. You can't have a negative measurement. And so this model is a bit ridiculous in that sense. And it's probably not going to pose a big problem in this particular case because a Curl index of kind of 6 or 8 is also impossible. But in some cases that you'll encounter, you will end up potentially fitting a linear model to your data that predicts unrealistic values. And that can be problematic for you. And so what we want to do, instead of fitting a linear model to this case, is actually use a generalized linear model. That's going to better allow us to kind of overcome the limitations and the restrictive assumptions of linear modeling and just make a more realistic model, right? Even though our residuals looked good, there wasn't anything clearly in violation. The actual model fit, we can clearly see that this model's doing something that's unrealistic, and we don't want to do that. And so let's use a generalized linear model instead.